So you guys humor me. Here's a front wall, here's the floor, and I want you to treat, excuse me, this is a side wall. I want you to treat the intersection side wall and the floor as my x-axis. The front wall and the floor as my y-axis. And the intersection of these two walls as my z-axis. This is a way in which I can refer to three number lines about axes, x, y, and z, in 3 space so I can locate points in 3-dimensional space. Or maybe if I'm going to draw this on the inkboard, I'm in a little bit of trouble because I'm trying to draw a 3-dimensional coordinate system in a 2-dimensional flat inkboard. You know I'm going to have problems with that, right? Because I'm drawing a higher dimensional image in a lower dimensional space. Some of my angles, some of my right angles will not look like right angles. So the x-axis is coming straight out of the inkboard. Here's my y-axis. Here's my z-axis. And yet, indeed, it is true that that right angle doesn't look very right when it comes to you and I sitting in this classroom looking at the inkboard. Just like if I were to bring in the classroom a 4-dimensional object, some of those right angles would not look like right angles, would they? You guys ever look, those of you who know me, you ever look at my office, look at my shelf, that red thing? That's a 4-dimensional cube. But I built it in our space, 3-dimensional space, so some of my right angles don't look like right angles. Wasn't that a name for a 4-dimensional cube? Hypercube. Hypercube or a tesseract. A tesseract, yes. Hyper.
So, that looks like a nightmare to me.
What?
having to draw that is just horrifying.
Oh, you've seen nothing yet. Give me another week or two. We'll be drawing surfaces in 3 space.
So like, let's say theoretically I can't draw worth a damn. Anybody who knows me knows this is a fact.
Don't worry about it. With the withdrawal date's not for another couple of weeks.
Oh, Jesus.
Jesus.
Are you going to give us isometric graph paper or something on the test when we have to like draw something in 3D space?
Gosh, I never have, but I suppose I can consider that.
Bring our own.
Of course you can. Yes, of course. Yeah, absolutely. So if I asked you guys to consider locating the point, 1, 2, 3, how would you locate it? Come on, humor me. How would you locate it?
1 on the x-axis, 2
So you walk 1 unit along the x-axis, then 2 along the y-axis, then 3 along the z-axis. So everybody, watch me with my colored pens. With my colored pens. And again, I know this looks a little bit awkward, but in blue, if I walk along the x-axis 1 unit, in a green, walk parallel to the y-axis 2 units. In a red, walk parallel to the z-axis 3 units. There would be location of the point 1, 2, 3. Sorry for drawing that on red. I didn't mean to. It's going to be black. And of course, you guys don't mind which way I represent points, do you? It's all the same thing. It's all the same thing.
No.
No, I don't think it's the same thing. I made a mistake. I think these are different. I think this is representing a vector emanating from the origin 3-dimensional space, terminating at that point that I labeled in red. So there is a difference. Just like back in math, what was your favorite math class? Math?
D.
D, you had quadrants in the 2-dimensional space. Now I'll have, not quadrants, but octants. And I give up on numbering them carefully. But if I'm sitting in V1 octant for which x, y, and z coordinates are positive, I refer to it as my first octant. Just a bit of vocabulary. So you guys, what did we do last time in class? We talked about the distance formula and midpoint rule, or midpoint formula. Oh, but we did that in 2 space. Let's jump higher.
So
Yes.
is that is the line connecting the vectors supposed to be coming from the origin, or is it supposed
Yes,
to
and
be
if I'm
coming
being too sloppy, Brad, I'm so sorry. I really
Okay.
meant this vector to be emanating from the origin
Oh, okay.
and terminating at that point that I labeled in red.
from? Okay.
My apologies.
I was just wondering if it was supposed to come from the beginning of the vector path or the origin.
But you guys and Eric, I mean, I think when it comes to a lot of surface and 3 space, things are so important in mathematics and physics because it describes so many different phenomena. I mean, I know when I was in graduate school, there's a lot of talk about the universe being in the shape of a hyperbolic paraboloid. You guys ever heard of that? No. A shape that kind of looks like this, where cross-sectional slices are parabolas and hyperbolas. kind of interesting, by the way, you guys, you'll be able to draw this in a couple weeks.
Okay.
Carefully, it's hard to, X, Y, Z system. But what's interesting about something like maybe the universe being shaped like this, is that if you really want to connect this position to this position, what you have to do generally is travel through our universe and get over there. Or maybe if you got the power, we can kind of maybe bend this universe, bend the shape a little bit, and maybe create a
Wormhole.
wormhole to get from one position to the other just by jumping in the higher dimensional space.
So a two-dimensional cross-section of that looks like a parabola then, and a three-dimensional...
Depends on where you are.
Oh,
If I take a two-dimensional slice right here, I think there'll be a downward shaped parabola.
okay.
But if I took a horizontal cross-sectional slice here, I think that would give me a hyperbola. It depends on what cross-sectional slice you have.
Okay.
Or you can also contract space too, like an accordion.
Absolutely. I think it's the same idea, really, in the end.
Now, does any of this happen in real life, or is this all theoretical?
Well, get enough black holes together in one place.
Like a what?
There are many phenomena that can't exist without looking at shapes like this. I even think talking about higher dimensional space has many applications. And I even think the higher dimensional spaces could have the higher dimensional components being spatial, not just something else like time, which is what Einstein really insisted on. So now, I guess it depends on who you are, but as a mathematician, I have no issue whatsoever in doing mathematics in higher dimensional space. Matter of fact, it doesn't even matter what the dimension is, the mathematics is the same. Well, with the exception when you jump into infinite dimensional space, then things become a little bit different. But that's beyond the scope of this course. We won't go there. Oh shoot, what did I say I want to discuss distance? So everybody, x-axis, y-axis, I'm too high, just a minute. Down below. X-axis, y-axis, z-axis. You guys help me. Rectangular solid?
Yes.
And if this is a rectangular solid, let me talk about this point right here. I'll label as A. And let's just go coordinate be, I don't want to be specific. Can I call it x1, y1, z1? You guys help me with this. If I label this point B right here, aren't its coordinates clearly going to be the same? And these are points, not vectors. I can't hear you.
Not Z.
Oh, you're right. I think that vertical distance I travel on the z-axis to get to that point B is going to be different than z sub 1, so let me give it an alternative name. I'll call it z sub 2. This time, no tricks. Are you happy with x1 and y1 being the x and y coordinates respectively?
Yes.
What about this point here? If I label this point C relative to B, what's the only thing that changes? Yeah, I think it's just the x value. Can I give it a new name? I'll call it x sub 2. But I think the y coordinate's the same, and the z coordinate's the same as the point B, not the point A. And lastly, if you guys allow me to label this point right here, I'm running out of letter, where am I at? D? Then I think all the coordinates are the same, x2, y1, z2, well, with one exception. I think the y coordinate changes. So can I relabel that as y sub 2? You guys, I'm not giving you the punchline yet. I'm taking very small steps. But with my purple pen, do you guys not agree that we can talk about this distance right here?
Yes.
Because I think in purple that distance is this easy. It's using the Pythagorean theorem within this triangle, that's a right triangle down below, is the length of this leg squared plus the length of this leg squared. That would give me the length of what you see in purple squared. Do you guys agree? But I think the length of this leg right here, look at the coordinates. They're all the same except for the x's. I think this length right here in black is this. Now look at the distance between C and D. X coordinates the same, Z coordinates the same. Oh no, the Y coordinates are not the same. So I think the distance between Z and D is nothing more than the difference between Y2 and Y1. So that in purple, relative to everything I discussed last time, in purple, I think that purple length is the square root of x2. Okay, so you can't see this anymore. Sorry. I don't imagine I got another purple pen. Oh, I do. Holy cow. line segments is I like blue. I think the length of that blue line segment is the square root of x2 minus x1 squared plus y2 minus y1 squared. Oh shoot, you guys, I just wasted your time. We've already done this. That's not what I meant. So, more colors. In green. Do you guys agree this length is this? So I think in red, the length of this line segment will indeed be the distance between two arbitrary points, I'll call them A and B, whose x, y, and z coordinates are different. And to come up with that length that you see in red, recognize that I've got, shoot, another nifty little right triangle. I will yet again use the Pythagorean theorem. And I think the length of that red line segment, all equal to D, can be interpreted as nothing more than the square root. The sum. The squares of the lengths you see in blue and the square of the length you see in green. Oh no, you guys, I don't like it. It's too sloppy. Can I clean it up a little bit? I think the square and the square root undo each other, and therefore the distance between 2 points in the Cartesian or in the XYZ coordinate system is merely the square root of the sum of the three squares that are indeed the differences in those 2 points' x coordinates and their z coordinates. Are you guys with me? It's a tiny little extension of the distance formula you and I have in two-dimensional space. That's why it looks so darn simpler. I just added one more component within the Radicans position, but I came to class and proved it to you. Now, what the heck is going to happen in four-dimensional space? The same darn thing. You're going to extend the radicand by adding one more term, namely plus W2 minus W1 quantity squared. And that'll be how you and I will compute the distance between 2 points in four-dimensional space. And we can jump into n-dimensional space, but like I said, as long as n's a finite real number.
What happens if n's not?
If n ends up being infinite, a lot of the underlying mathematics just changes dramatically. That's why when you guys take a typical, I won't embarrass you, but how many of you have taken 33? Just a couple of us, 3 or 4 of us. It doesn't matter what dimension you're in as long as n is some positive integer. The only problem is when n becomes infinite, then the underlying mathematics changes dramatically. That's why in this typical, across this country, a typical differential equations linear algebra course, you restrict yourself to finite dimensional spaces as opposed to infinite dimensional spaces. Besides that, now the question is, what level of infinity? Because I assume you guys know that there's infinitely many different levels of infinity, right? They're called transfinite numbers. You're laughing.
This is kind of a nerdy question, but
Sure.
I thought there was only 11-dimensional space.
I think, tell me if I'm wrong, I think you're thinking of what Einstein did not answer, which is when he was trying to unify all the fields of mathematics. He wanted to create a unified field theory. And so the question is, can we come up with enough dimensions to encompass all the subfields of physics? So we can deal with magnetism, large bodies, small bodies, et cetera, et cetera. And some people will just say, well, why don't you just consider 11 or even a higher dimensional space to accommodate all those issues? As a mathematician, that's just gimmicky. That's just saying, well, let's bring the dimension up here so we can talk about these things. That's different than saying, I've got an 11-dimensional space in which each dimension represents something distinct and spatially.
Well, if I recall, that's string theory and like what? Oh well, it's like it came from string theory because I think they also say 11 dimensions, and I don't know. There was something about like if you look at it with in the 5th dimension, you can explain electromagnetism.
But that's simply attaching electromagnetism into one of those dimensions, and that's why I'm saying is I shouldn't say this in front of you guys.
You're just
It sounds gimmicky. And as a mathematician,
you're shoehorning it basically, right?
yes, I agree with that. I agree completely.
How I've heard it explained, and I don't understand it myself, that it's that they are spatial dimensions, but they somehow don't exist except at very tiny distances, and so beyond those distances, the qualities up here as electromagnetism as the different forces.
It still sounds like we're wedging something in there to make it work, and that's why I use that word gimmick. As opposed to thinking of actually a physical item in higher dimensional space. Let me give you an example. Do you think at any position in this classroom, the temperature is the same?
No, there's
No,
gonna be
I don't think so.
slight variation.
Yeah, I think there, it isn't. So maybe I could build a whole new variable instead of x, y, and z. I have a w to represent a temperature function evaluated on a position x, y, and z in three-dimensional space. I just built myself a function of 4 variables where the fourth component may not be spatial, but it represents something like the temperature at a given position in this room. Maybe I can add another component representing the pressure at a given point in this room, or maybe a bigger environment like above this country.
Yeah, I just have a quick question on time though, because that seems to be the oddball dimension. Because
Why is it oddball?
Well, at least the way we experience it is only ever in one direction.
Oh, I was hoping you'd say it's oddball because what's time?
Oh, yeah.
No, I'm serious. As a mathematician, I'm an abstract algebraist. Everything for me is based in set theory. As a mathematician, every time I try to define a set, it leads to a logical contradiction. Physicists have the same problem. You can't find a physicist, I hope, not that I know of, who will define time for you. Time is extremely difficult to define.
Isn't time made up?
You could say man has a perception of time. But if you want to talk about time as its own identity, particularly for those of us who represent time as a fourth dimensional component, then you'd want to define what time is. And it's just too difficult.
And isn't the reason that we bring time up is just because of like relativity and stuff? Because of
But doesn't that make it a more complex conversation? Because now we need to know how time gets warped.
yeah.
With space
well,
as
I mean,
well.
that was the whole reason time got brought up as a dimension in the first place, was because it's affected on a relativistic level.
Yes, I agree. I agree.
Well, on the human perception level, there's studies in
But
psychology that talk about that.
Why do we say subjective? Is it because we just run into a brick wall and we try to define it?
Well, we all experience time in different ways, and then, I mean, one of the experiments that I know of is when the astronauts leave, time's different for them,
Yes.
so it's, I mean, and then you, like athletes, they say that like time slows down in certain situations for those people, but does time slow down for like everyone then, or how does, so it's subjective.
Ma'am, I'm sorry, I talked right over you. Do you have a question?
Well, I was just gonna ask, you talked about how it's kind of gimmicky or whatnot, like when you just assign a dimension to
Yes.
consider, is it kind of like just so you can have a, kind of like assigning a point, like just so you have a frame of reference?
I think
to
that's
talk
exactly
about?
what it is, yes.
So, these theories is that, I'm just trying to understand what you're talking about, these theories, they're just like ways to assign a dimension in order to talk about it? Or?
I agree completely. Yes. And also to bring all these subfields of physics in one conversation.
Yeah, but then, yeah, potentially all the theories should be able to be combined into one.
Well, that's what
talk
Einstein
about it.
thought. That's what Einstein thought, but he never finished that process. And nobody's picked it up. Well, nobody else has finished it either.
Well, what about quantum mechanics? Doesn't that?
Well, quantum mechanics is one of those sub-dimensions.
Yeah, doesn't it throw a wrench into all sorts of other fields?
Why just need the relationship to, yeah, particularly with bigger body physics, creates a huge problem.
General relativity.
Yeah, I agree.
The problem they have with unifying all the theories is that on scales, electromagnetism and magnetism and the nuclear forces are almost infinitely stronger than gravity is.
Yeah.
So when they have different scales, they have to add more dimensions, and by adding more dimensions, they can change things like electromagnetism operating on r squared, and they can change all the different constants so that they're relatively equal to each
Yeah.
other, and they can.
Yes, yeah, exactly. And you know, mathematicians are just as stubborn. We try to create our own unifying all subfields of mathematics. We call it category theory. That's what I did a lot of my research on. So, yes.
So bring us back to this.
Yes. Sorry.
The blue line is your magnitude of the two is of your magnitude of the resultant vector of your two x and y vector, the displacement that you have there.
Can I put more words in there? I think that blue line segment, if you think of it as a vector, is the resultant vector of adding arrow BC to arrow CB.
In that, yeah. yeah, your displacements in that direction.
Yes,
Sure.
not that I literally talked about vectors when I went through the process, but you could, yes, I agree.
And then D is the addition, you're adding those two displacements, the one you just come up with, and then your Z displacement. to get
Yeah,
to
the one I drew in green, I agree. So I think what you see in red, you could interpret it in terms of vectors as a resultant vector from what you see in blue with what you see in green, if it's going in the appropriate direction. But I avoided the whole issue of direction, because I was just simply dealing with real value distances. So everybody, this is in our back pocket. How to compute the distance between 2 points in the Cartesian in the XYZ coordinate system. Oh, shoot. How about this? If I have 2 points, P and Q, with these coordinates, do you guys think seriously, I'm not trying to be silly, can I hand wave this one? I just think this is so obvious, and tell me if I'm wrong. We do indeed now know how to compute the distance of those 2 points.
Yes.
It's just if I want to compute the midpoint of the line segment connecting these 2 points, wouldn't that just be an ordered triplet? Whose entries are of, the arithmetic mean of their x coordinates, comma, the arithmetic mean of the y coordinates, and comma, yet again, the arithmetic mean of the z coordinates. My justification is that if when you look at the midpoint of the line segment that I labeled, that I drew in red, I do think the midpoint has an x coordinate, that's just the average of these x positions here on the x-axis. Same with the y-axis, same with the z-axis. I think that's trivially true. So, can you guys help me out with this? Do you think I can look at one example before we stop? What the heck does that look like?
That looks like a vertical line, point on a number line.
It's a plane.
Oh, what do you mean plane? What plane?
An infinite set of points where x equals 1 and y and z can equal anything.
Good. This says nothing about y and z. They can be anything you darn well please. But x has got to be equal to 1 for all those points. And so I think in the x, y, z coordinate system, this is a plane parallel to the y, z coordinate plane, but 1 unit lifted above the inboard. So that all the points in this plane have a y coordinate of, I don't know. But a z coordinate of, I still don't know. But an x coordinate of +1. Did you guys see that? Well, that was a baby step. That's a nice, clean, easy plane. We'll augment that dramatically. You guys, I said so little. Do you mind if we just take the night off? Not doing homework.
Okay.
Fine.
Oh, no.
But when you come to class on Friday, we'll have a